Jai Hind. Today we are going to discuss groups. We will take and here in particular we are taking binary operation. Then we'll talk about properties of operations. Then we will define semigroups, monoid, and finally we will discuss the properties that must be true for being a group. And then we'll end the lecture with some examples. So let us start with the concept of operation. Let us take an non-empty set, that is S. An operation on S is a function from S cross S to S. Means we are taking here binary operation. So we will take elements from S cross S. S cross S is the Cartesian product. So it means we are taking two elements, A and B, both are from S. So this is denoting for first element and this is for second. So Cartesian product we are talking about. So we are having a pair of element, and on that pair of element we will apply the operation, and whatever we will receive as the result, that will also be from the same set. Then we call it an operation. If let me say the operation is star, then we can we represent the star operation as A star B. A and B are our operands, and for simplicity we may simply use sometimes AB only. So what we are having here, a set S and an operation star. It is denoted by S star. It means the operation is defined on this set. Now as we are saying that our both the operands will be from set S and result will be in S only. So we can say that we are having two elements, A and B, belonging to S, and then we are doing operation, and what it is giving us AB, that is also belonging to S. So this property is called closure property. So in short we can say that if closure property is true for an operation on a set S, then it is an operation. And here we are taking two operands, so that is our binary operation. So let us take the concept, let us make the concept clear with few examples. So I have taken here a set of positive number, that is set of natural numbers, positive integers, n. So if we talk about n and I do addition on two positive integer, what will I get in result? That will also be positive integer. The addition of two positive integers is always positive. It means in set of natural number, if I do operation plus, then it will follow the closure property. So it is an operation defined on n. Same way if I take multiplication. So if I take two numbers which are from set of natural numbers, and actually these are positive integers. So if I do multiplication, the multiplication of two positive integers will also be a positive integer, and it will be a positive integer means in the same set. So it is also a function. It is also an operation. What operation is? It is a function which maps S cross S to S. Means it will take two elements from S and the result will also be in S. That is closure property. Now if we talk about subtraction. If I take two positive integers, 3 and 4, and what I am getting here, that is -1. So as -1 is not present here in the same group, so this is not operation. Subtraction is not an operation on n, that is the set of positive integer. Again, if I say I take the division, then 3 by 4. If I take 3 by 4, then it will give us some value which will have fractional part. It is not a positive integer. Okay, so subtraction and division both are not operations. So these are the example. Let us understand with one more example. I am taking two sets here, A and B. A is set of even integers and B is set of odd positive integer. Even and odd positive integer. A is having positive integers which are even, and that is B is odd. So if I talk about addition, in addition what will happen if I take set of even integer and I do addition? So any two positive integer which are even, if I take, I'll again get even integer in the result. Okay, so it is closed under addition. If I take multiplication of two positive integers, it will also be a two positive even integer, it will also be even integer. So A is closed under addition as well as multiplication. But if we see B, in B, if I take two odd integers, I am not getting odd in the answer. If I multiply two odd integers, definitely I'll get a positive odd integer. Okay, so B is closed under multiplication but not addition. So here we have seen that if we see the addition and multiplication, that is operation with set of even integers, but addition is not an operation with set of positive odd integers. Okay, so this way we can find out that our operation is defined here or not. Now after definition, we'll talk about properties. When we are having an operation, what properties it may follow? First one is associative law. An operation on a set S is said to be associative if for any ABC from the set we have A star B star C is equal to A star B star C. It means we apply the operation on AB first, then the result is done with C, or if we do with B and C first and then do the result with A, we'll get same answer. For example, if I am having addition, then 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. What does it mean? It means either I will add 1 and 2 first, then result will be added to this, I'll get 6. Or what is the option? I add these two first and then add to 1. So 2 plus 3 is 5, 1 plus 5 is 6. I'll get the same answer. Okay, so this is associative law. When we have set of positive integer and addition operation, it is associative in nature. Second is commutative law. An operation star on a set S is said to be commutative if for any element A, B in S we have A star B is equal to B star A. It means left and right operands may be interchanged. So if I take two values and I do 3 plus 4 or 4 plus 3, I'll get same answer. So our set of positive integer, if set of integers is given simple and we define addition, we can add anyway in any manner A plus B or B plus A. That is commutative law. That is A star B is equal to B star A. So this is the two properties we have studied here, associative and commutative. Next is identity. Identity element. Let us consider an operation star on a set S. An element E in S is called an identity element for star if for any element A in S, A star E is equal to E star A is equal to A. It means if there is one element such that if we do operation with that element, we'll get our second element in the answer. For example, if I take 0, if I take set of integers and operation is addition and I take 0, I add 0 to anything. The element to which we are adding 0 we will get in answer. Any value we can take. In general, if I take a plus 0 is equal to 0 plus a. So in short, we can say 0 is additive identity. Same way we can talk about multiplication. In multiplication, let me take 1. If multiply 1 with any value, I'll get that value in the answer. For example, 3 into 1 is 3. 4 into 1 is 4 and a into 1 is a. So that is our identity element. And in general, we call that multiplicative identity. 0 we call additive identity and 1 we call multiplicative identity. Now next property is inverse. Inverse exists or not. So suppose an operation star on S does have identity element. So inverse will be checked when we will have the identity element. Suppose an operation star on a set S does have an identity element T. The inverse of an element A in S is an element B such that A star B is equal to B star A is equal to E. It means there is one element B for A such that if we do operation of A with B and we get in answer the identity element. Let us understand with the operation of plus. My additive identity is 0. So if I take any positive integer A or any integer A, for positive I'll take negative as the value. So if I take any integer that is A and I add minus, I take minus of this. So both are inverse to each other. Why? Because A plus minus of A will give me 0. That is identity in the answer. Okay, so that will be the inverse element for integers and plus operation. Okay, if we talk about multiplicative inverse in integers. Okay, so when I'll get what is multiplicative identity, that is 1. So for A, if I have to find out the multiplicative inverse, that should be 1 minus A, because A into 1 by A could give me 1. But when I am having some integer, let me say 2. So 1 by 2, that is multiplicative of inverse of this, is not an integer. So for addition, if I talk about set of integers with addition, the additive identity was 0 and inverse will be minus of the element. For example, if 2 is the element, minus 2 will be the inverse. If minus 2 is the element, then 2 will be the inverse. But when I see the multiplicative identity, the multiplicative identity is 1. I multiply 1 with anything, I'll get that in answer. The other element will be in the answer. Okay, but when I see this, then identity is there, but 1 by 2 is not inverse. Okay, so when I take set of integers with multiplication, it is having identity, but it is not having inverse. Now we will talk about the definitions of our algebraic structure. So we'll start with semigroup, then we'll define monoid, and then we'll discuss about the groups. So S I am taking as non-empty set and operation is star. So I'm having the operation star and S is my non-empty set. So what is a semigroup? If S is having only the associative property holds true, okay, if S is called semigroup if the operation is associative. If the operation with the set holds the associative property, then we call it semigroup. Okay. If the operation has associative as well as the identity element, then we call it monoid. If we talk about the set which we took on the last slide, that is set of integers and multiplication operation. So multiplication is associative in nature according to integer arithmetic, and 1 is an integer such that if I multiply any element with 1, I'll get that element in answer. So Z with multiplication forms a monoid. It is a monoid. It is associative as well as it is having the identity element. Now the final thing, that is group. What is a group? Here we denote in general groups with set G. So let G be a non-empty set with binary operation star. Then G is called if the following axioms hold. So what are the properties required for an algebraic structure G star to be a group? First is associative law. For any ABC in G, we have A into B into C is equal to A into B into C. So what we are doing, the operation A star B is applied on A and B. For simplicity, we are denoting it with AB. So when I am having AB, so the operation is implied. Whatever be the operation, for simplification, we are using this notation. So A star B star C is A star B star C. We have just talked about. If identity element is there, that is, there exists an element E in G such that A star E is equal to E star A is equal to A for every E in G. Inverse. For each element A in G, there exists an element A star in G, which we call inverse of A, such that A star A inverse is equal to A inverse star A is equal to E, the identity element. So if it is associative, it has the identity property and it has the inverse property, then the set, the non-empty set G with the binary operation star forms a group. These are the axioms that are considered for being a group. One more thing we will add here in a continuation of the definitions. Abelian group. If G with star is a group, group means it is associative, it is having the identity element, it is having the inverse element. Okay, it is associative, identity and inverse is there, so it is a group. So if it is a group, okay, a group G is said to be abelian, and it also has the commutative property, that is A star B is equal to B star A for all AB belonging to G. Then we say that group G is abelian. It is an abelian group. So if we consider our example of set of integers with plus operation, okay, it is associative because on set of positive integers, the operation plus is associative in nature. Second, it is having the identity element 0. 0 belongs to Z. This is additive identity. Third, if A is integer, then minus A is also an integer. And if we add A with minus A, if we apply addition on A and plus minus A, then we'll get identity element 0 in answer. And we can see that the plus operation is commutative also. if we add A to B or B to A, when our A and B are integers, then it follows the commutative property. So it is an abelian. The set of positive integers with plus operation forms an abelian group. And if we talk about Z multiplication, we have already seen it is associative. It follows the associative property. It is having the identity element 1, but it is not having inverse. 1 by A doesn't belong to Z. Inverse element doesn't belong to Z. So it is only a monoid. So this way we can check that what our set forms with the operation. So we have taken here another example. The rational numbers Q form a group under multiplication or not, we need to check. So if we talk about rational numbers, the rational numbers are those numbers which can be written in the form of P by Q, where Q is not 0. P by any number that we can write, where P and Q are our values, our whole numbers, our integers, then if we can write that in terms of P by Q, then that is a rational number. So as we can see, associative property holds for this. How can we check that? The associative property we can check with 3 numbers. And what operation we are taking here, that is multiplication, and we know that multiplication on these numbers are associative in nature. That we can verify also by taking 3 numbers, 3 rational number P1, Q1, P2 by Q2, and then we multiplying it P3 by Q3. If we do other way around, that we multiply firstly P2 by Q2 with P3 by Q3, we'll get on both sides P1, P2, P3 divided by Q1, Q2, Q3. So this follows the associative property. If we talk about then the second property is identity element. If I say multiplicative identity is 1, so I need to check that, can I write it as P by Q form? Yes, 1 can be written as 1 by 1. So if I multiply any rational number with this number, definitely I'll get that in answer, P by Q. So that will give me identity element. Okay, now third property we need to check is inverse. What is inverse element? Inverse element is P by Q. We need in answer 1. So if we multiply it with Q by P, we may get in answer 1. But it fails for the case of 0. Because 0 can be written as 0 by 1. But we cannot define Q by P for this. So inverse doesn't exist. We do not have inverse for 1. So it doesn't form a group, it just form a monoid. Same way, if we take a subset of 2 by 2 matrices with non-zero determinant. Non-zero determinant means inverse exists. So if we take matrix multiplication, we know that matrix multiplication by matrix algebra is associative in nature. Second, we have identity matrix. Identity matrix of 2 by 2 matrices will be 1, 1, 0, 0. And we know that it has non-zero determinant. And because it is having non-zero determinant, so for each A inverse will also exist. And if we check the last property, what is the last property? After being a group, we can check for abelian. So if I have two matrices AB, then AB is not equal to BA, because from matrix algebra we know that matrix multiplication is not commutative in nature. So it is not an abelian group, it is only a group. Okay, so these we have done few examples. So in this particular lecture, we talked about basic properties of operations. Then we defined groups, and before groups, we talked about semigroups and monoids. Thank you. Jai Hind.